In the last lesson, we examined prime numbers. During that lesson, I suggested that prime numbers are the building blocks of all integers. Now, the meaning of that statement is best illustrated by the following theorem. It says that any integer greater than 2 is either prime or can be expressed as the product of prime numbers. So, for example, 21 can be expressed as 3 times 7, where 3 and 7 are both prime numbers. We call this the prime factorization of 21. Similarly, 60 can be written as 2 times 2 times 3 times 5, where all of the numbers are prime. This, incidentally, can be written as follows. Now here's the prime factorization of 250, and here's the prime factorization of 7,644. An important point about the prime factorization of a number is that it is unique. For example, this is the only way to express 7,644 as the product of prime numbers. As you will see later in this lesson, we can learn a lot about a number by examining its prime factorization. So we need to become proficient at expressing numbers as the product of prime numbers. I'm going to show you one technique for doing this. Let's say we want to find the prime factorization of 60. Now 60 is not a prime number, which means we can write 60 as the product of two numbers. What are two numbers that multiply to be 60? Well, one pair of numbers is 6 and 10. Let's examine these two numbers. First, we have 6. Is 6 a prime number? 6 is not prime, which means we can write 6 as the product of two numbers. Two numbers that multiply to be 6 are 2 and 3. Both of these numbers are prime, so we'll circle them to remind us that we can't factor these two numbers any further. Now what about 10? Is 10 prime? 10 is not prime, so we can write 10 as the product of two numbers. Two numbers that multiply to be 10 are 2 and 5. 2 and 5 are both prime, so we'll circle them. We have now broken 60 down into several prime numbers. So 60 will equal the product of the prime numbers found at the ends of the tree. We can write this as follows. Now this technique can be applied in several different ways, and it will always yield the same prime factorization. To demonstrate this, let's find the prime factorization of 60 again. Once again, we know that 60 is not prime, so we want two numbers that multiply to be 60. This time we'll use 3 and 20. When we examine these two numbers, we see that 3 is prime, so we'll circle it. Now 20 is not prime, which means we can write 20 as the product of two numbers. It doesn't matter what two numbers we use, just as long as they multiply to be 20. How about 10 and 2? Now 10 is not prime, so we'll leave that for the moment. 2, however, is prime, so we'll circle it to remind us that we can't factor this number any further. Now 10 is not prime, so we can rewrite it as the product of two numbers. Two numbers that multiply to be 10 are 2 and 5. 2 and 5 are both prime, so we'll circle them. We've now reached the ends of our branches. At this point, we can see that 60 equals the product of the numbers at the ends of the branches, which we can rewrite as follows. Notice that this product is the same as the product we got from the first attempt. Now, finding the prime factorization of a number is a very useful technique, so be sure to practice it on several large numbers. At this point, you might be wondering how prime factorization is supposed to help us tackle integer property questions. Well, the prime factorization of a number tells us a lot about that number's divisors. Here's what I mean. Let's say that we know the prime factorization of 1540. From this, we can see that 2 must be a divisor of 1540. We know this because in the prime factorization of 1540, we have a 2. This tells us that 1540 is equal to 2 times some number, which means 2 must be a divisor. Similarly, we can see that 7 is a divisor of 1540, and 11 is a divisor as well. Also from the prime factorization, we should see that 4 is a divisor of 1540. Now, there might not be an actual 4 in the prime factorization, but if we recognize that 4 is equal to 2 times 2, then we can see that there is a 4 hiding as 2 times 2. Similarly, we can see that 77 is a divisor of 1540. This is because 77 is hiding within the prime factorization as 7 times 11. Finally, we can see that 110 is a divisor of 1540. This is because 110 is hiding within the prime factorization as 2 times 5 times 11. Using the prime factorization, we can also see that 3 is not a divisor of 1540, since there is no 3 to be found in the prime factorization of this number. Similarly, 8 is not a divisor of 1540. We know this because 8 is equal to the product of 3 2's. So for 8 to be a divisor of 1540, there would need to be 3 2's hiding within the prime factorization. Since the prime factorization has only 2 2's, we know that 8 is not a divisor. One last example. 33 is not a divisor of 1540, since 33 is equal to 3 times 11, and the prime factorization of 1540 does not include a 3 and an 11. Now, in an earlier lesson, we saw that there are several different ways to say that one number is divisible by another number. We'll now add another line to this list. If x is divisible by y, it must be the case that y is hiding somewhere within the prime factorization of x. So, for example, if we are told that 6 is a divisor of w, we know that the prime factorization of w must have a 6 hiding somewhere. Now, since we're talking about the prime factorization of w, the 6 will be hiding in the form 2 times 3. Similarly, if we are told that r is divisible by 88, then we can conclude that there must be an 88 hiding somewhere within the prime factorization of r. Of course, that 88 will be hiding in the form 2 times 2 times 2 times 11, since this is the prime factorization of 88. So, to summarize, the prime factorization of each number is unique. The prime factorization of a number can help us determine its divisors, and if some number k is hiding in the prime factorization of a number, then k must be a divisor of that number.